Hey, it's Tim the Tutor here with Free Test Prep Online, and in this video we'll be reviewing stereochemistry, in particular how to determine R and S absolute configurations at stereogenic centers. Assigning absolute configurations to stereogenic centers can be a little tricky, so we're going to start with the simplest case first, and then we're going to move on to do the more complicated examples. So first we're going to identify a stereogenic center. Once we do that, we're going to assign priorities 1, 2, 3, and 4 to each of the atoms bonded to that stereogenic center. And when I say atoms, I mean it. I don't mean the entire group, I mean the individual atom that is directly bonded to that central atom. We prioritize based on atomic number, with the highest atomic number getting the 1 priority. In the simplest case, we cannot have two atoms that have the same atomic number. For that is a step where we need a tiebreaker. So in the simplest case, we're not going to worry about tiebreakers. We'll cover that later in this video. Next, we also must have the 4 priority oriented on a dash. If the 4 priority is not on a dash, again, we'll have special things to do in that case to make this easy. And again, that'll be covered later in this video as well. If we do, in fact, have the simplest case, the next thing we do is simply draw curved arrows from the 1 priority to the 2 to the 3 and then back to the 1 in a circular manner. If the arrowheads are moving clockwise, we're going to assign an R to the stereogenic center. If that's difficult for you to remember, you can also think of it as the arrows are going in the direction to the right from the atom on the top. So if an atom is on the top, it's going right. This is an R stereogenic center. If the arrowheads are moving counterclockwise, we're going to assign an S instead. So let's look at these 2 molecules that are depicted here. These molecules appear to be enantiomers, or non-superimposable mirror images. We can confirm that they are in fact enantiomers by assigning an absolute configuration to both of them. One of them should be an R, and the other one should be an S, if they are enantiomers. So we're going to follow our instructions here. First, we're going to identify the stereogenic center in both of them, which of course is this central carbon atom. And now we're going to assign priorities to the 4 atoms directly bonded to it. So we have hydrogen, carbon, fluorine, and oxygen. And we do this by atomic number. The highest atomic number out of those 4 atoms is fluorine. Next, we have oxygen. Third, carbon. And last, we have the hydrogen. This is in fact going to be our simplest case because no 2 atoms are the same, and the 4 is oriented backwards on a dash in both of them. Next, we're going to draw curved arrows from the 1 to the 2 to the 3, and the 3 back to the 1 in both of the molecules. If the arrowheads are moving clockwise, or like I said, if they're moving right from the top atom, in this case the top atom is the carbon, if they're moving to the right from the top, we're going to assign an R stereogenic center. So the molecule on the right-hand side is going clockwise, or again, from that 3 priority, which is on the top of the molecule, it is going to the right. So that one is an R. On the other one, we are going counterclockwise, so the first molecule here is going to get an S. And that's all you need to do to assign absolute configuration in this simplest case. Unfortunately, the simple case doesn't always occur. Another case, called the tiebreaker case, results when 2 or more atoms bonded to the stereogenic center are the same. In this case, of course, we need to use a tiebreaker. The instructions on this page show how to go about doing the tiebreaker. Now, if you want to pause the video and jot this down or take notes, feel free to. But I think it's better to go through an actual example of how to go through these, as it'll make a lot more sense than just reading these or writing them down. Essentially, what we're going to do is every time there's a tiebreaker, we need to go 1 atom further out. So I'll show you what that means in the next slide. The molecule depicted here is fairly complex around its stereogenic center. The stereogenic center, of course, being this central carbon atom. So normally what we would do is we'd prioritize 1, 2, 3, and 4 based on atomic number. But it looks like that central carbon is bonded to 4 different carbons, so we have a 4-way tie, because no 1 carbon has a greater atomic number than any of the other carbons here. To break the tie, we need to make a list of what each of those 4 carbons is also bonded to, other than that central carbon, of course. So to help us with this, I'm going to arbitrarily assign each of these carbons a letter A, B, C, and D. This is going to help us keep track of what each of them is bonded to. So we're going to make a table, carbon A, carbon B, carbon C, and carbon D. And now all we need to do is list out all of the atoms that carbon A is bonded to, other than that central carbon, which they all share. Carbon A is bonded to 2 hydrogens that aren't drawn and 1 carbon. So I'll go ahead and mark those right now so you can see it. So here's the carbon that carbon A is bonded to, and then we have the 2 hydrogens that aren't drawn in the skeletal structure. So in other words, carbon A is bonded to 1 carbon and 2 hydrogens. If we look at carbon B, it is also bonded to 2 hydrogens that aren't drawn and a carbon. So carbon B also has a carbon, a hydrogen, and a hydrogen. Looking at carbon C, we have the same situation. We have a carbon, a hydrogen, and a hydrogen directly bonded to carbon C. And then carbon D is interesting because it has a double bond. So it is bonded to 1 hydrogen, but how do we treat that double bond? Well, for the purposes of prioritizing, we treat a double bond as if we were bonded to 2 carbons. So a double bond to a carbon, for the purpose of prioritizing, would mean carbon, carbon, hydrogen. Of all the atoms that we've listed, now we simply pick the one that has the highest atomic number. But of course, we have a 4-way tie. So we're going to actually cross out 1 carbon from each of these lists. Of what's remaining, what has the highest atomic number? And of course, that is carbon. So we have a winner for our first tiebreaker here. So we're going to give carbon D priority number 1, because of what was remaining, we had carbon, which has the highest atomic number. So we're going to give this the 1 priority. Of course, now, after we've done the 1 priority, we only have hydrogens left. So we can no longer use those to break the tie. In this case, we're once again going to have to go 1 atom further out. So let's extend our table. I'm going to mark in green 1 atom further out from carbons A, B, and C. The green atom above A is bonded to an oxygen and 2 carbons. The green atom to the right of B appears to be bonded to 2 different carbons and 1 hydrogen. And then the green atom below C is bonded to 1 carbon and 2 hydrogens. We don't need to worry about carbon D because we already prioritized it as the first priority. So looking at all of the atoms we just listed in this next set of atoms in our table, which one has the highest atomic number? Well, that goes to oxygen. So we can confidently say that carbon A is going to get the number 2 priority. Now let's compare B and C. Both of them have a carbon, so those share a priority, but carbon B, or at least the next atom out from carbon B, has another carbon that it bonded to. So that means carbon B is going to win priority over carbon C, which has those 2 hydrogens 1 atom further out. So we can give the 3 priority to carbon B, which leaves us with the 4th priority on carbon C. So now we can go ahead and fill these in. 2, 3, and 4. Now that we have our 1 through 4 priorities and we have the 4 priority already facing backwards, now we can draw our arrows from the 1 to the 2 to the 3, and the 3 back to the 1. Note that this is going clockwise or right from the top side of the molecule. So that means we can assign this the configuration of R. In our final scenario, we're going to go over the wrong orientation case. And this occurs when the 4 priority is not oriented on a dash. So steps 1 and 2 remain the same. We identify a stereogenic center, and we prioritize 1 through 4. So let's go ahead and do that for the stereogenic centers on the 2 molecules shown on the bottom of the page here. So we have our stereogenic center on the first molecule there, and then on the second molecule, we have it here. Now I'm going to go ahead and draw in the missing hydrogen, and I'm going to draw that on a wedge in this position right here because we already have the nitrogen on a dash. Now we're going to go ahead and assign priorities to all 4 of the atoms bonded to each of these. Chlorine on the left molecule is the highest atomic number, so we're going to give that the 1. Second, it's fluorine. Third, it's oxygen. And fourth, we have carbon. On the molecule on the right, oxygen is going to get the 1 priority. Next is going to be nitrogen. Then we have the carbon, and then we have for this hydrogen. Now note that the 4 is not oriented backwards in either of these molecules. So what we have to do is either manipulate the molecule by rotating it around in our heads to get it so that it is facing backwards, but that is way too complicated, and it's very difficult for most people to think in 3 dimensions, so rather we're going to apply a trick instead. And that is step 3. We're going to draw the opposite configuration of the molecule by switching the positions of the group with the 4 priority and whichever group is on a dash. When we do this, we are in fact drawing a brand new molecule that has the opposite orientation of the original molecule, because again, we're switching the position of 2 of the atoms. So when we do this for the first molecule, we're simply going to switch the 4 with whatever is on the dash. So the chlorine is going to remain in the same position. However, the CH3 group is now going to be on a dash. That's going to put the fluorine over on the left, and the oxygen is going to stay exactly the same. On the molecule on the right, I do not want to redraw that entire molecule, so I'm going to show you a little trick. All we're going to do is we're going to draw a stereogenic center, and we're going to have our 4 connections to it exactly in those same positions that they're drawn originally, but instead of drawing out the entire group, what we're going to do is simply put a number in each of those spots. And again, we're switching the 4 priority with whatever is on a dash. So the 4 priority used to be on the wedge, and what was on the dash was the 2 priority. So instead, I'm going to put the 4 priority on the dash, and I'm going to put the 2 priority on the wedge. The 1 and 3 are going to remain the same. Again, if we just write the numbers in here, this is going to prevent us from having to draw this entire molecule. So once again, what did we just draw? We just drew a brand new molecule with the opposite configuration at the stereogenic center of the original molecules. So in other words, these are not the same. So now that we've done that, we're going to prioritize the new molecules. So again, the chlorine in this new molecule gets the 1. The fluorine gets the 2. The oxygen gets the 3. And the CH3 or the carbon here gets the 4. On the molecule on the right, we've already put in the numbers, so we don't need to reprioritize. Now we're going to give an R or S configuration to each of these new molecules because the 4 is facing backwards on them, so we can use our system where we draw an arrow from the 1 to the 2 to the 3, and the 3 back to the 1. So this looks like an S configuration. That means the original molecule is exactly the opposite configuration because we drew a new molecule that was intentionally opposite in order to prioritize it better. So originally we had an R. And if we look at the new molecule for the one on the right, 1 to 2, 2 to 3, 3 to 1, this is counterclockwise, so this is also an S. And when we look at the original molecule, that has to be the opposite. So the opposite of S is, of course, R. And that's how we assign absolute configuration to molecules where the 4 priority is not oriented on the dash. If you got something out of this lecture, please feel free to like this video and subscribe to this channel. If you have any questions or comments, leave a message below. And last but not least, if you want more help or want easy access to valuable organic chemistry resources for free, be sure to check out the notes underneath this video with a link to join our community.